Hey guys, welcome back to another A-Level Maths Made Easy video. This time we're looking at implicit differentiation. And again, this is another topic that isn't always taught particularly well. Instead, they normally just teach you the rules and then that's it. But I'm going to show you exactly where the rules come from as well, because that will lead to a bigger understanding, or a deeper understanding, sorry. And that'll actually make you get this better and make you be able to answer questions a lot more easily, because the questions for this, once you understand what you're doing, are extremely easy. So the differentiation that we do is really minor. In fact, it's probably easier than the other differentiation that we've heard about before. This is also super useful in real life, so if any of you are going on to do some kind of maths-based degree or medicine, something like that, this will be used as well. So, before we get into it, just to let you guys know, most of the people that watch these videos are not subscribed, so if you could consider subscribing if you found any of this useful or any of my other videos useful, that would be perfect. But let me go into what is the difference between implicit and explicit. Well, when we have something that is explicit, that means that it is very obvious and it is clearly defined. So for example, an explicit function will look something like this. You'll have y equals, let's say, x squared plus 2x plus 4. I've clearly defined what y is and what x is, clearly. An implicit function is a function that is not clearly defined. So let's say I had something like, well, what I'm actually going to do is I'm going to rearrange this equation. I'm going to move everything over to the left-hand side. So y minus x squared minus 2x minus 4 equals 0. Now, it's not clear what y or x depends on, or if it's y or x that's the actual function, right? So we have here, y's and x's all mixed together. The reason why this is a little bit trickier is when I differentiate this, I mean, if I differentiate using the usual rules, you'll notice that we don't actually get the same thing as what we do up there. So if I differentiate all of this with respect to x, I'll get 0 here, and I'm left with just minus 2x minus 2. Whereas here, we actually get a slightly different function. First of all, we get dy by dx. We don't get dy by dx over here. The reason is because when you differentiate constants, you get 0. That might be something that you're aware of. So when I differentiate 4, you get 0. The thing is, when I differentiate y, I don't know that it doesn't depend on x. So for example, because I've given you the original equation, y depends on x, in which case when we differentiate it, it doesn't equal 0. That's where the dy by dx comes from, because we're saying that we'd have to differentiate y with respect to x, and that gives us, 2x plus 2 in this case. But in this case here, because it's not clearly defined what y is, if it is a function of x or if it's a constant, so we don't know if it's a constant or a function. And because we don't know that, when we differentiate, we can make mistakes. Now, the good news is, there is a way that we can actually differentiate this and do it all nice and neatly. The first thing I'm going to do is I'm going to differentiate the top just to prove to you that this gives us actually the exact same thing. We get 2x plus 2. So we're looking for dy by dx equals 2x plus 2. Now if I differentiate both sides of this, let's have a look at what happens. The first thing I'm going to do is I'm going to differentiate everything that isn't y. So we get minus 2x minus 2 equals 0. And of course, if we move this over to the other side, we get 0 equals 2x plus 2, which is not correct. So how do we get the dy by dx? Well, here's what we do. I'm going to call y a function, and I'm going to call it, let's say, f. F of y equals y. When I differentiate this, we get df by dy, I get the number 1. Now, I don't want df by dy, I want to work out what df by dx is. So, and again, I'm going to explain why do I want df by dx. I want df by dx because I'm trying to differentiate this function with respect to x, right? Logically. So, df by dx, well, on the numerator, we'd have to have df by dy. But then, we have to somehow cancel out. Remember, this is what I was trying to teach you guys last lesson, and with the chain rule as well, is what do I need? Well, I want df by dx, so I need to cancel out the dy. So I'm going to put dy on the top. And I want a dx on the denominator, so I'm going to put dx there. So that gives me that df by dx is equal to 1 times dy by dx. So in other words, when I differentiate y, I get dy by dx. That's where the dy by dx comes from. Then if you just move everything over to the other side, you get dy by dx equals 2x plus 2, which is the exact same thing as we get when we have an explicit function, which is the point. So when you have a bunch of y's and x's, because it might not just be one y and one x, it might be a bunch of different ones, and they're not expressed as y equals something or x equals something, you have to use implicit differentiation because you don't know if y and x depend on each other. We can't assume that they don't, which again is really useful for a lot of real life stuff. So what's this rule that I was talking about? The rule that I was talking about, it follows like this. If you ever differentiate a function, in fact I'm going to write this slightly differently, with respect to x, but that function is a function of y, then all you do is you have df by dy times dy by dx. Now that might look a bit weird, so we're going to go through a few practice questions of course, but essentially whenever you differentiate something that's y, you differentiate it normally and you times it by dy by dx. That's it. That is the only thing that you have to do. So let's go through a couple of examples just to make sure this makes sense. So we're going to do a ton of examples here, okay? Now the first thing you might notice is that there is no like equation as such, right? It's not y equals or anything like that, because again, this is implicit. So remember what we do. We differentiate it as if it's normal, so we're going to make it 4. If I differentiate 4y with respect to y, I get 4, then we just times it by dy by dx. That's what that expression becomes. Again, remember, we're using this original thing here. If we're differentiating a function of y, we differentiate with respect to y, and then we times it by dy by dx. So same thing here. When you differentiate sine, you get positive cos, right? Well, you get 2 in this case. So you get 2 cos 2y times dy by dx. That's it. That's all we're doing. And again, if we wanted to use the chain rule to do that, again, remember we have the function of y equals sine 2y. So we differentiate with respect to y. And then again, df by dx will equal df by dy times dy by dx. So again, we just times that by dy by dx. And this is true anytime you differentiate anything that has y in it. The next type of question, and this is honestly the most common type of question, is find dy by dx in terms of x and y in each case. So here, again, we're going to differentiate this with respect to x. So we get 2x. What would the next thing be? Differentiate with respect to y, so it becomes 2y. And then times it by dy by dx equals 0. Now they want dy by dx, so we're going to rearrange for dy by dx. So I'm going to minus 2x on both sides. We get 2y. Dy by dx equals negative 2x. I'm going to divide both sides by 2y. We get 2y, dy over dx equals, well, we have 2 divided by 2, so that's just negative now, x over y. So you can always rearrange to actually get what dy by dx is, and you may need to factorize. So I'm going to show you one of those a bit later as well. So again, we're finding, this is just part B of the question here, find dy by dx. So we differentiate with respect to x. So here we'd have 4y cubed dy dx equals 2x minus 6. So divide both sides by 4y cubed minus 6 over 4y cubed. We could divide everything by 2 as well, just in case they wanted us to simplify. We get x minus 3 over 2y cubed for dy by dx, which is fairly nice. So as promised, I'm going to give you one that's slightly harder. Now, I want you to think for a second, what makes this more tricky? Why am I saying this is difficult? And I'm going to explain it to you in 3, 2, and 1. This uses the product rule. Why? Because x and y timesing each other, remember they're both functions of x. So we have to actually use the product rule twice for this question. So we're going to use it for the left-hand side. So we're going to say that u equals x, v equals sine y. So that means du dx is 1, dv dx is, well, it goes to cos, right? But then it's cos y dy by dx, because again, anytime we differentiate y with respect to x, we need to add that dy by dx to make sure we're not missing anything. And again, we do it with the other side as well. So we have u equals x squared, v equals cos y, du dx is 2x, dv dx is negative sine y, and again dy by dx. So we've done the product rule twice. So it's going to be the cross terms multiplying, so it's going to just be sine y, and then it's going to be plus x sine cos y, sorry, dy by dx. We're going to have a plus, and again we're going to do the cross terms. So we have 2x cos y, and we have negative x squared sine y dy by dx equals, well, differentiating that's nice and easy, it just equals 0. So now we have to actually, don't forget the question was, work out what dy by dx is. So how do we do that? Well, what we need to do is we need to put everything with dy by dx on one side. So it's already on the left hand side, so I'm not going to bother changing it. And I'm going to move the sine y and the 2x cos y over. So we're going to have x cos y, because I want to keep that here, dy dx, minus x squared sine y, dy dx, equals, and there's just going to be a bunch of negatives, so minus 2x cos y, minus sine y. And hopefully this kind of brings you back to GCSE when you had rearranging harder formulas, where you're moving everything that you want to one side, and now we're going to factorize out dy by dx. So I'll factorize dy dx, and you get x cos y minus x squared sine y equals this disgusting stuff. And then just divide it over, and we're finally done. Now, yes, this is absolutely bloody hideous, but remember, that's okay, right? Maths can be hideous sometimes, but this is the correct answer. We're doing everything great, and that's it. Now, just so you guys are aware, I wanted to take a quick aside. In mark schemes, if you ever see an answer that has all the same bits as you but different signs, so instead it's 2x cos y plus sine y over negative x cos y plus x squared sine y, or of course the denominator could be swapped around, so x squared sine y minus x cos y. These two things are indeed equal to each other. All they've done, if you'd like, is they've times the top and bottom by -1, which is an equivalent fraction, so it's totally okay. Now, this is actually something that's quite interesting, and some of you that have done or will do university interviews for something related to maths or physics, you may get given something like this to differentiate. So this is actually quite it's a pretty good question. It's only ever come up once, but it shows that they can give you differentials that you've never seen before. And that is completely allowed, that's completely fine. And I'm going to show you how you do that. Now, luckily in this question, they say by first taking logarithms as a bit of a hint. Now, I will say, in the actual exam, it just said this. Differentiate this and show that it equals blah, 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 blah. So, I'm going to show you how to do this by first taking logarithms, so it makes sense to do that first. I would advise just taking ln. And now what can we do before we get started? Well, we can use the power rule to bring that forward. And now we can actually do the implicit differentiation. ln a is just a constant, so we're going to treat it as if it was the number 3 in front of x. In fact, I'm actually going to rewrite this to make it super, super clear as ln a x. So we can treat that exactly like we would treat a number 3, a number 4, a 5, whatever, because it's just a number, it's just a constant, because it says here a is a positive constant. So now, implicit differentiation. When you differentiate this with respect to y, you get 1 over y, but remember, we need to times it by dy dx. And that just equals, well, ln a. And that's it. So all we're going to do now is we're going to dy dx, we're going to times both sides by y, and we get dy by dx equals y ln a. Now if we actually have a look at the question, it just says find an expression for dy dx in terms of a and x. So a and x only. Well, y is the same as a to the power of x. So that means dy by dx is the same as a to the power of x ln a. And that's where that result comes from, if you've ever seen that before. It is something that's hopefully taught fairly regularly. But here's another way that implicit differentiation helps, because differentiating this normally is a pain in the butt, I can tell you that. Now, the reason why I mentioned that you may have seen that result before is these are two other questions based on the same thing, where it says differentiate 3 to the power of x. And the funny thing is, in the mark scheme, it literally just said, it just used this result. So it said 3 to the power of x ln 3. So you could literally just write and get the right answer, because this is a standard result that we've derived, which is very nice, right? We derived a result. How cool, how exciting. But if you follow the exact same steps, you'll get the exact same thing. But for part B, I'm actually going to show you how to do something like that. So again, we're going to say that y equals 6 to the power of 2x. We're going to take the natural log, just like we did before. 2x. And I'm going to bring the 2x to the front. But then I'm also going to just shove it at the back, which is, you know, exciting. So we have ln y equals ln 6. And I'm only doing this just to make super clear that ln 6 times 2 is just a constant. So when we differentiate, again, differentiate with respect to y, we get 1 over y. Then we need to times by dy by dx, because it is a function of x, equals just, no it doesn't, equals just, let's call it 2 ln 6. Yeah, that works. Times both sides by y, and again we're just going to sub in what y is. Which they told us at the beginning, well, we set at the beginning that y is equal to 6 to the power of 2x. And you are allowed to do this. You're allowed to say that y equals this, because all we're saying is that 6 to the power of 2x is a function of x, which it is, obviously. We could have called it any other letter in the alphabet if we wanted to, but because we're doing implicit differentiation, I thought it'd make more sense just to leave it as dy dx, just to, you know, not confuse anyone. That will become 2. I want to put this in brackets, because something that I see sometimes, which I'm not going to lie, it makes me physically ill, is people would write this as 12 to the power of x. That is completely wrong. Do not do that. This is 2 times 6 to the power of x. Just leave it as that. Again, you can sub in some numbers to prove it if you want. If x was 2, you'd have 6 squared is 36, times 2, which is 72. 12 to the power of 2 is 144. Not the same at all. So be really careful with that. And yeah, let's move on. So once we've done that, I'm hoping this makes a bit more sense. Again, I do think that in some cases, just from when I've tutored other students and things like that, this isn't taught super well. Instead, it's just given as a rule. And the problem with the rules is they don't always make a lot of sense. And when they don't make sense, it's very hard to learn them. Whereas if you understand where it comes from, you've probably realised that you know the rule without actually memorising the rule, because you understand it, you understand where it comes from. So hopefully that's helped you a little bit. If you have found it useful, again, please consider subscribing, because it does help me out. And my link to my website and to my email address is in the description in case you have any questions or want tutoring or anything like that. But I will leave you to your exam revision, and I'll see you later.